something we do every semester. We tend to have something on the order of 8 or so speakers in the lineup. It's a series that's jointly organized by the Environment and Community Master's Program and the Schatz Energy Research Center. And we have a lot of talks, a whole series of talks this semester. All are at 5:30 on a Thursday, and all are here in this room. And so look for these posters. You can also find information online at the Schatz Energy Research Center's website, www.schatzlab.org, and I think also on the Environment and Community Master's Program website. So please look for other talks in the series, and hope you'll join us on other evenings as well. Tonight, we are really pleased to have Belinda Batten here with us. She is in the Mechanical Engineering Department at Oregon State University and is director of the Northwest National Marine Renewable Energy Center. They're doing some of the really leading work in the United States around offshore renewable energy, focusing both on wave energy and offshore wind. And we see this as a very promising technology here on the West Coast, and we see OSU playing a leading role there. So we're really happy to have Belinda here to speak. So without taking up more of the time, I'll just pass it over to Belinda. Please give her a warm, humble welcome.
Thank you. Thanks for having me. Thanks. So is our mic on? Okay, good. So it's a real pleasure to be here today, and I want to thank Arnie for inviting me to come down. And there's an acronym I'm going to use that you might get used to, and that's NNMREC. So instead of trying to fumble through the Northwest National Marine Renewable Energy Center every time it comes up, we'll just call it NNMREC. So NNMREC is a partnership between Oregon State and University of Washington, and as of just this week, we're expanding to University of Fairbanks and University of Alaska Fairbanks. And what I want to do today is explain to you what we've been doing with marine energy and some of the opportunities that we hope it's providing for our energy future. So at Oregon State University, we're trying to use this to make this, preserving scenery that looks like this, not creating scenery that looks like that, and not seeing anything like that. And that's my story. Well, obviously that's not my story has more to it than that, because you didn't come here for a 1-minute talk. But anyway, I like those slides. They come from a partner of mine in Oregon named Jason Bush, who's the director of the Oregon Wave Energy Trust. And the reason why I like it is it talks about what we're doing, how we're doing it, and what our intent is. So now I'll elaborate on that. So NNMREC started in 2008 when U.S. Department of Energy put out a funding opportunity announcement to create centers that would look at marine hydrokinetic energy technologies. And one of the centers is in Florida. They're the Southeast Center, and they focus on extracting energy from ocean currents, so the Gulf Stream. As the Gulf Stream is passing the land, you'd put a turbine in the water and the turbine would turn and create energy. They also are doing some work on ocean thermal energy. Second center is in Hawaii. Hawaii is looking at wave energy. There's a test facility on the Marine Corps base there for wave energy devices, and the Hawaiian Center works with that test facility, and they're also doing some work on ocean thermal. And the third center was us, the NNMREC Center, and that was started by my colleague Bob Pash, who's in the audience. Oregon State University was focused on wave, and University of Washington was focused on tidal. And if you think about the resources that are available in those two states, that makes some sense. Oregon has wonderful wave resource, not unlike what you've got here off of the Northern California coast. We've got wonderful electrical transmission systems, and so it just seemed like a prime area to get involved in this kind of thing. So when Department of Energy put these centers together, they didn't want us to just be pointy-headed basic research centers like some universities tend to be. They wanted us to look at how do you advance these technologies by filling in the gaps in understanding in the science and the engineering, by helping to inform the regulators who are responsible for environmentally sound decisions when these devices go in the water, How do you help inform the government who funds them about how to fund more research? And we educate students. And when they gave us this mission, they put together a series of research activities they wanted us to focus on. And we've evolved since then. The top effort of developing suites of test facilities has grown into an effort all its own that I'll talk a little bit about. And then you can see there's several different research pieces there that they were interested in from the technical side. How do you optimize device performance and how do you optimize arrays? How do you look at environmental effects of these devices? How do you quantify wave resource? And most of all, if we're going to put these in the water, we want them to be reliable and sustainable because otherwise it's not going to do any good for looking at an energy future around this technology. And so if you think about all these efforts that they gave us as part of our project objectives, it's really focused on how can we look at this technology from the standpoint of reducing its cost of energy. That's really the ultimate goal. So when we look at how the research and education partitions in NNMREC, I think about three legs of the stool. We have the technical side, all the work that's being done largely in the engineering side of the house, a little bit in the oceanography side of the house. We have the environmental side, that's the environmental effects, the environmental interactions. And then one part that I think people sometimes forget is the social side. None of this technology is going to be adopted into our oceans or into our estuaries or whatever without looking at the social effects and the social dimensions. And I know from talking with Arnie that Humboldt State has some focus on policy, and the human dimensions is very critical in the policy side, which I've been learning firsthand. And as an engineer, they don't train you in how to do these things. So I'd love to spend time telling you about all the things we're doing, and obviously I can't. And so I'm going to structure my talk today where I talk about testing efforts, and I talk about some research efforts. I'm going to talk about the wave side of the house, talk a little bit about the tidal side of the house, and talk a little bit about the work we're headed into in offshore wind. So I told you our testing facilities had really grown to the point where they're really a focal point. So much so that my co-director at Washington, Brian Pelagi, and I got together and said, we really need something to focus the tidal side, and we're going to create an effort called PMEC, the Pacific Marine Energy Center. How many of you guys have heard of the European Marine Energy Center? Anybody? Okay, so if you say to someone, I'm going to go test at the European Marine Energy Center, folks who know that will know it's the premier site in the world for testing both wave and tidal energy devices. So Brian and I said, well, let's create an analog in the Pacific Northwest. We'll call it PMEC. It's a place where we can test tidal devices and wave devices, and we're going to go, so EMEC tests things only in the open ocean water. Since we're universities with testing facilities on campus, we'll include those test facilities in PMEC. So PMEC is going to go from scaled facilities at our universities all the way through open ocean testing. And so I want to talk a little bit about what we're doing at PMEC. First, and I'm going to focus the first part of this, as I mentioned, on catching the wave side of the house. And I just took this on the way down today. It was such a gorgeous day on the way down. I think this one was at Bandon today. So looking at my audience, my guess is you know something about wave resource. But in case you don't, to get everybody on the same page, when people say, why are you doing wave work in Oregon, the wave resource is always going to be best on the west side of a continent, and it's better further away from the equator. And so if you look at places that are orange or kind of burgundy, those are going to have pretty good wave resource. And if you can find Scotland on the map where EMEC is, you'll see that it's burgundy. And then if you look off the west coast, you see, hey, that's a great place for wave energy. So it's natural that we'd be looking at this sort of resource here. I'd mentioned that we're looking at it in Oregon because we've got great resource. Washington has great waves too, but they don't have the electrical transmission infrastructure. So it makes it a little bit tougher for them to jump in head first into this technology. When people talk about wave energy devices, most people think that you have a wave energy device goes up and down in the water. That's the prototypical concept that I run into. But one of the things that you'll find when you say what's being done is you find wave energy devices today come in all different shapes and sizes and flavors, and anything you can do to extract energy from the ocean with the waves, people will try. This is a device called the Oyster from a company called Aquamarine, and they're in Scotland. Their device operates by sitting near the shore and have a flapper go back and forth as the waves surge over top. On the left, you've got a picture of the device in the manufacturing plant. On the right, you've got an artist's rendering of what they think a suite of them would look like in the ocean. This is a device called an oscillating water column. They come in two variations. This variation sits on the shore, say a jetty, that kind of thing. If you've ever gone along the coast and stopped and looked at the spouting horns where the waves come in and the water goes flying through a hole, it's that same kind of idea here where the wave will come in and it'll push air through a turbine, and the turbine will spin. As the wave goes out, it sucks air back out and a turbine spins, and that turbine spinning will generate the electricity. This is a device called Limpet, and it's been on the island of Islay in Scotland for about 10 years, I believe. Here's an example of yet a different kind of technology. It still involves a spinning turbine. It's called the Wave Dragon, and it's an overtopping device. The water comes up and over the device and then goes out and makes a turbine spin. It's been tested in Denmark for a couple of years. This is a device that I know our Oregon regulators get concerned about, what kind of environmental impact this might have on fish that could get caught in a turbine. So these are kind of the questions that arise. And then here's a device called the Pelamis device. This is one that's actually fairly advanced from the standpoint of how much it's been tested. A couple of those devices have been tested at EMEC for quite some time, and it operates by sitting on top of the water and going up and down like this as the waves go underneath, and then there's hydraulics inside that create energy from that wave motion. So just from this page, you can see all sorts of shapes and sizes and how they operate. The next slide, I'm going to focus on devices that have had some connection to Oregon. This device is by Ocean Power Technologies. It tested in Hawaii. I mentioned that there's a test site at the Marine Corps base. This was a 40 kilowatt device and it was in water for quite some time. They had plans to test a 150 kilowatt device off the coast of Reedsport, and in fact into an array of 10 devices and beyond that. At this point, the company is kind of in limbo, and their plans in Oregon are uncertain. But this is that device that goes up and down with the waves like most people would think a wave energy device does without knowing anything more about what's going on. This is a device by a company called Columbia Power Technologies. This is one of my favorites, and not because they hire lots of OSU engineers, which they do, but they're a company that didn't stay married to their initial technology. They started out with a device that was a buoy that heaved up and down, and in fact, that was a device that was built with OSU's help as a joint partnership. But as they've gone through their testing regimes, they've stepped back and said, what might do a better job of extracting energy? And again, lowering that cost of energy. So they went from having a device that just went up and down to splitting that float and having two pieces that went up and down like this, increasing the motion that you would get. And then they realized by having two floats that were made up a circle, they're missing some of the wave that's hitting it. And so they then busted out to having floats that are square. And this is a picture of them testing in Puget Sound, 1/7 scale device. And as a result of that test, they found that their floats would come up and go down, and they had end stops. And they realized they were losing a lot of energy through this stopping. And also it was affecting the reliability and survivability of the device because there's a lot of fatigue when you have this stopping motion. So they redesigned their device yet again, splitting their spar into two pieces, and now their floats can flip 360 degrees around through that spar, reducing the fatigue on the device, extending its life, and not losing all that energy each time the floats stop. So if I were going to try to develop a device myself, one of the big lessons I would take is try to look at them and see that they're a company that's really learned from the testing cycle, going back and doing some redesign and testing again. So 2 thumbs up for me on them. Now, for the people who complain that they don't want to see these stinking devices out on their water, this is an interesting concept out of Oregon State University from about 20 years ago. This was a device that started out as a senior project. To hear them tell the story, they tried to test it in a wave tank at OSU that was broken. They went to the head of civil engineering and asked if they could fix it and put the device in and test it. And the head of civil engineering said no. So they have a video of it, and you ask if how they got their video. They snuck into the building late one night and fixed the wave tank and filmed their device, and then drained the water out and broke it again and left. So, when I tell this story to my freshman engineering class who are trying to deal with ethical dilemmas, I ask them to analyze the ethical dilemma around this, given that this device was just put in Oregon waters today to test. So there's for future discussion. This device works by sitting on the bottom, and as the waves go over the top of the ocean, there are changes in the pressure column. And pressure changes in the water column is what I meant to say. And you can think of this as having airbags on the bottom that depress, and as the air goes back and forth, a turbine spins, and that's how electricity is produced. The company is called M3 because it's run by 3 guys named Mike. Truth. And then here's the last device. This is a device from Finland. It's called the Penguin. This is a good device for the people who say they don't want any external moving parts. It looks a little bit like a ship's hull, but it's not symmetric. And as the device sits in the water and goes back and forth in the waves, and they want it to be really, really, really tippy, there's a pendulum inside that swings around. And that pendulum inside that's swinging around extracts energy. They've been testing at EMEC. They've talked to us about coming over to Oregon. So that completes, it certainly doesn't complete all the devices that are out there, but it gives you 8 very different devices to show a lot of the diversity that people are trying to cook up around wave energy devices. Okay, so testing. At Oregon State, we've got some scaled wave tanks that are really some of the premier ones in the country for testing devices. We have a large wave flume that's on the bottom center there that's about 100 meters long and about 5 meters deep and about 3 meters wide. People will come and stick their device in there and test it, and they can see what happens under a variety of wave regimes, including 100-year storms. Both M3 and Columbia Power tested devices there, and then we've had some graduate students test some concepts. On the right, we've got our tsunami wave basin, which is a directional wave basin. It's not nearly as long and skinny. It's got 29 paddles along the back that can operate independently to create some very realistic wave regimes. And that was a picture of one of Columbia Power's devices done in an array. I think this test was done right before they did their 1/7 scale in Puget Sound. That tank is smaller. It's only about 7 feet deep. But it gives you a sense of where people can come and test the concept, see what kind of energy is being produced. Is the device operating dynamically the way you would expect? Those little lights on top of the Columbia devices are part of a dynamic measurement system called phase space that came out of the movie industry that allows us to get very fine data on what the devices are doing in terms of their dynamic motion. After the scaled wave tank, people want to go out into the open water. I was going to say open ocean, open water. And we initially thought they'd want to go right into the ocean, but what we found is our partners at University of Washington have a great asset, both being close to Puget Sound, which is where Columbia tested, and this is Lake Washington. And so Acilla Power is a company in Seattle that has a device that extracts energy from the ocean by stretching some piezoelectric actuators. Piezoelectrics, as they stretch and as they compress, produce voltage. So Lake Washington was a really great place for them to test because it was nearby. It wasn't as vigorous as the open ocean, just a safe place to kind of get your feet wet, pun intended. The place that we developed at Oregon State, and this was under Bob Pasch's leadership, was what we're calling the North Energy Test Site. So if you hear somebody talk about PMEC NETS, the Pacific Marine Energy Centers are testing, and NETS is the North Energy Test Site. This is a square nautical mile on the border of the territorial sea and the outer continental shelf. So we're in state waters. You can kind of see the territorial sea line there. The depths vary between about 45 meters and just a little over 50 meters. And this site is not connected to the electrical grid. What someone would do to test there is to connect their device via an umbilical cord to our mobile ocean test berth that we call the Ocean Sentinel. So you could think of the Ocean Sentinel as being a surrogate for the grid. We tested a device called the so here's a picture of the Ocean Sentinel. It's got some wide-angle cameras on it. So it's kind of a funny picture. Up at the top, you've got our first device that we tested, which was called the WET-NZ. It's on its side. It was pulled out by a tug. And then here's a picture of it once it got upright, connected to the Ocean Sentinel. And so the WET-NZ has this float that goes up and down in the water. The limitation on testing this way is the Ocean Sentinel is only capable of doing devices up to about 100 kilowatts. And a lot of the developers want to go upwards of a megawatt or even more to reach what they're considering to be the utility scale devices. So Ocean Sentinel is great for a developer who doesn't mind if their power output is scaled. They're in a full ocean environment, so they get to see what happens in these vigorous waves like we have off of our coast, like you have off of your coast. But it's not the full meal deal for these developers yet. So, as I mentioned, the gold standard right now for testing is the European Marine Energy Center, or EMEC. It's up on that green box up there on the top of that map. It's in Orkney, Scotland, which is a really cool place to be if you've never visited there. And so that what we're trying to do now with PMEC is to create a wave energy test site that would complement what they're doing at EMEC. People often ask me, well, I don't know if I want a test facility, what does it look like? And so these are pictures I took when I visited EMEC. I'm standing very near the shore and I'm just going around in a circle taking pictures. So that's a building where their switchgear, their devices, or their instrumentation for measuring how much energy is being produced are housed in that. The local community didn't want it to be an eyesore, so they created it with a green roof and with nice stone surroundings on the building itself. As you move over, you see transformers like this that belong to the device developers who are testing. You keep moving around, you see this great bluff called Buoy. I pointed out because I'm going to take a picture from there in a minute, and then I'll show you a picture in a minute, and then you can see where my reference point is. And if you keep moving around, or you go inside, there's the switchgear inside the building. And if you keep moving around, here's what we saw. This was the Oyster. Remember the Oyster? That's the first device I showed you. This is out in the water. And at the point of reference of how big is it, there's a boat nearby that's just sort of a normal fishing size boat, nothing too huge in size. So it gives you a sense of what it looks like in the water. And then if you go up on that bluff that I showed you, over on the left is the Pelamis device. That's the sea snake. One of the things I know from talking with community members is they get very concerned of what the viewshed is how the viewshed is going to be impacted. What am I going to see? Well, that Pelamis device is about 600 feet long, and it's about a mile away, and I'm up. So I was surprised at actually how minimal the view of the Pelamis was, given how big it was, given that I'm up, and a mile really isn't very far if you think about where a lot of these devices will be deployed. And then if you look over a little bit to the right of center, there's the Wellow Penguin, that one that kind of looked like a ship with a bunch of corner marker buoys and that kind of thing around it. So that gives you a sense of what these look like in the water. Okay, so Pacific Marine Energy Center, PMEC SETS, the South Energy Test Site that we're developing. Here's our cartoon of what we think it's going to look like. We are busy but we will be busy putting 4 cables out to the site. The site will be about 5 to 6 nautical miles off the coast. It'll have 4 berths. Each berth will be a place that one kind of device can test. If a developer said, I wanted to see what happens if I put 3 or 5 of my devices together, they can do that. We'll have a power pod that you can connect multiples of the same kind of device. Then when the cable comes onto shore, we're going to have a utility connection and monitoring building, just like that one I showed you from EMEC. and then the power will go on to the grid. And we're pretty excited about the progress we're making on this. We've been busy working on the regulatory side. We have a lease application in for the ocean with the federal agencies that control that. And the way this came about was through an extensive community outreach process that involved 4 different communities in Oregon. We eventually down-selected to Newport and Reedsport. And then this was a picture of a map that the Newport community gave us when they submitted a proposal to us and said, we really want your site, here's where it should go. And one of the most interesting moments for me was that square, or that rectangle on the side there that says proposed siting area. That was drawn on a map by a group of fishermen. I walked into a room, they'd known we were working on this, we talked about what we needed in a site, and they rolled out the map and grabbed a Sharpie and said, let's find a site for Belinda. And so the lesson that told me was, in order to get to that point, you have to develop strong relationships with the communities, and you have to have dialogue, and you have to share your needs and listen to theirs and really engage. And it was a very productive and positive outcome to be able to get this site. So that's the testing in a nutshell of what we've been doing on the wave side. I want to move a little bit over into our research side. And again, I can't do everything, but I'll give you a little bit of a sense of the kinds of things we're doing. One of the things we find is we want to have models for devices. Simulation models so that we can predict how much energy is being produced, so we can predict the forces on devices, so we can understand life cycle and failure and fatigue properties. And so we had a graduate student who was modeling that Ocean Power Technologies point absorber, and she took and just built a basic physics model of the device looking at the dynamic behavior. She used MATLAB, she used Simulink, she used some other software out there that model wave forces. And the outcome of this is to come up with a simulation that looks something like this. So along the x-axis, we've got time. Along the y-axis, we've got displacements. So the one at the top, that red line, is a spar plate. That's essentially acting as a damper to keep your device spar fixed in the ocean column so that the float can go up and down against it. And so you would want that to be pretty still, and it is pretty still. That was a positive thing. The line that's kind of yellowish is the surface of the ocean. And she was using real wave data that she'd gotten from a data buoy that was out there. And then the blue is how her buoy's moving in response to that wave input. And so from that, she can then link up with various models for power takeoffs and understand what energy is going to be output. She can look at forces and analyze what's going to happen to this kind of device. We've had some electrical engineering students build an analog of this and test it in our wave tank. And one of the things we run into that's kind of difficult from a research graduate student perspective is a lot of the data from the developers is not open source. So if you want to try and use that to validate models, you can't get very far. And so that's one of the things we're trying to do at OSU is, as we're generating data, make it open source so other people can use it and learn from it. Here's another project that's being done. This is an example of one of, like the Wello, a vertical axis pendulum device, where as the device sits in the water and moves around, a pendulum swings. So we decided this is a pretty good generic kind of device. It's not very complicated to think about. It doesn't have a lot of moving parts. A good mechanical student in dynamics can generate a model for it. And so my student's been working on how to do that, and he's come up with a dynamic model, and he's now working on how might you control this device. You might say, well, control, why would you control it? Don't you just pop it in the water? But if you think about it a minute, if your device is out there and you've got waves that are going back and forth nicely and your pendulum size to go around well, that's great. But that's not really what the ocean looks like. You get these hiccups in your waves, you get these irregular waves, and it's possible that device might not just keep going like this, but it might go like this, and your pendulum kind of gets stuck. And if you were to put just a little bit of energy back in to keep that pendulum going, might that produce more energy as a net? And so that's one of the things this student's looking at. And so if you want to think about the way the control should look on this, ideally you'd want that pendulum to be up to, so I'm working from left to right on this graph. You want that pendulum to be up to be in a position to extract, be in a maximal potential energy state, so that as it rides that wave, that pendulum's going to come down, transferring potential into kinetic energy. And then as it goes back up over the next wave, you kind of reverse those positions. So he's looking at controls from that standpoint and has built a model where we can toss this into the wave tank and do some validation. Again, the goals are to develop some really straightforward dynamic models so we can simulate, we can investigate control concepts, and make all of this open source. Here's another example of some work that's been done at OSU. This has been done by one of our professors in oceanography, and there should be a video running, but I'm not sure it is. Does it look like anything's moving? It was supposed to play automatically, but we'll come over here and see if it works. Okay, so the challenge is, so first of all, let me tell you what the pictures are. The upper picture is just the Earth, cut in half, opened up. And she's trying to come up with models for wave resource. Down in the lower left, she's got essentially the upper quadrant of that map, so you can see the Pacific Ocean. And then on the right over here, she's got a slice of the Oregon coast. So if you're going to try and cite a project, you're going to try and understand the wave resource, you've got wind data, you don't have much else, and the wind buoys are very sparsely positioned. And so they're far from the coast. And so how do you take that very sparse data and make something of it that's useful for wave resource prediction? And so what she did is developed an approach where she's come up with a very fine grid that's fine enough up and down the Oregon coast to do good wave resource prediction. We're going to be tossing some instrumentation in the ocean next month that will gather data for a year and then hopefully validate her methods. But when just thus far, in comparing what she's done with wind buoy data, she's only off by about 10%. So she's been really excited to see how far this work has gone. When people ask me, oh, you can only predict waves for how long, a day or two? She can predict the waves really well for about 84 hours. So this bodes well for the folks like the utilities who want these devices to come online. How do they adjust to what's happening? It doesn't have the, oh, gee, now it's windy and I've got good wind energy coming on, and oh, gee, now it's not windy at all, I've got no wind energy coming on. The waves are much more stable. So that's really positive news. And there's the data about, I commented how she was very accurate. There's her plot about accuracy. Okay, so that's a lot of the technical side. We have a lot of other technical research, but I want to switch gears a little bit to the environmental effects, because this is an area where we've been doing a lot of at OSU. If you think about what could happen by putting a device in the water, all you have to do is talk to a couple of regulators for a while, and they'll make you afraid of all the different things that might happen. And it really opens your eyes to things that, as I think as a lot of engineers, the engineers I work with might not necessarily think about it straight off. So we've got some folks at OSU who are doing environmental work, trying to understand what's happening, and they're busy talking to regulators about what the fears and concerns are so that we can move forward with some understanding about what might really happen out there. So we've got everything from, you put these devices in the water, you're extracting energy from the ocean, and so maybe you're extracting enough energy that the sediment doesn't move the same way it used to. And not only would that change beaches, but it might change habitat for the critters that live on the bottom of the water, or bottom of the ocean. Similarly, in terms of habitat for critters, when you put something in the water like an anchor, that changes the habitat and you get artificial habitat building up, artificial reefs. Is that going to be bad for populations that expect their baby fish to be somewhere else? We have potential electromagnetic field effects to things like salmon that navigate using and are affected by the electromagnetic fields. You've got the acoustic effects of these devices in the water. if you have a device that's got a lot of mooring cables and they're in an array with a lot of mooring cables, is that going to provide an entanglement challenge for something like a whale? So a lot of questions to think about once you're aware of all these potential impacts. So the first thing that we do when we get in the room with the regulators and the environmental scientists is try and decide, out of all these things that could happen, where's the highest risk? Or where's the biggest unknown? And try to prioritize where we're going to spend our efforts and where we're going to spend our money. It wouldn't make sense to study something if you're not going to learn anything, for example. And it also doesn't make sense to study something if it's not that important and is not very likely to happen. So through discussions with the regulators and our scientists, we've come up with this list of 4 priorities. They are to study what happens with the benthic habitat, so that's the sandy bottom, as you put devices in the water, your anchors, those kind of things. Try to understand what interactions there could be with marine mammals, things like this entanglement potential, running into something and being trapped. Looking at the acoustic effects. Are these things so loud that they're going to get in the way of communication between dolphins or something along those lines? And then talking about the electromagnetic field effects. So in terms of the sandy bottom, we've got a faculty member at OSU named Sarah Henkel. She's our environmental research director for NNMREC. And she goes out and gathers critters. She takes grabs in the sand and counts what's in there. She looks at the things that lives in the sand. She looks at things that live on the sand. And she does seasonal studies, because one of the things that's important, if we want to understand what things look like now and what things look like when we put devices in the water, do we need to study once a year? Do we need to study once a quarter? So the kind of work she's doing right now informs those kind of things. How often will we need to study to understand, are the changes that are happening to those critters things that would have happened anyway just by seasonal variation, or are there things that we did by putting these new devices in the water? Here's some more pictures of the kind of things she does. She looks at the crabs, she looks at the fishes that live on the sandy bottom. Her students always look like they're having a lot of fun. But the pictures of Sarah, I've always seen her on sunny days. I can't imagine going out on a field run with her in the winter would be very much fun. At OSU, we've got some experts in whales. Bruce Mate is one of our professors at the Marine Mammal Institute. And it's really easy to get folks to watch whales and track what whales do. And so, fortunately, the community has helped us out with that. And what you've got a picture of here is the area around our North Energy Test Site and the gray whale migration paths. And one of the reasons we're interested in this is not just will they interact when we've got a device out there, but suppose a device is having a problem and we need to go out and monitor it and maybe pull it back in. It's good to know if the whales are going to be out there, because we would not want to schedule just regular maintenance if we could defer it to another time when the whales aren't there. And if we know the whales are there and it's necessary that we go out, then we know to be ultra careful and look for the whales, maybe have more marine mammal observers than we normally have. So when I saw this picture, I was really excited, because this is where our North Energy Test Site is, and our South Energy Test Site is on the left side of that red line. It's on the outer continental shelf. And the reason I was so excited is I said, oh great, there's not going to be any whale interaction at the South Energy Test Site, at our grid-connected test site. Well, guess where the whales go when they go south? They go on the left side of that red line. So it doesn't matter which test site we're in. We're either going to be dealing with whales going north on the one in the territorial sea, or we'll deal with whales going south on the outer continental shelf. One of the things we've been thinking about is what might we do to make sure whales don't come near our devices and near our test facilities. And so we've had Bruce Mate, who I'd mentioned before, and one of his colleagues working to develop a whale deterrent device. So just a little acoustic device that would sit out there and ping, not be very loud, not be very obtrusive, just trying to get them to move away. And so they've been busy working on that project, and they haven't fully analyzed the data yet in terms of the effectiveness, but we're hopeful that could be something that we could add to our suite of monitoring and environmental instrumentation. In terms of acoustics, I mentioned the issue that these devices are going to go in the water, they're going to make noise, or they're going to be too loud that they're going to disrupt things. So we have a faculty member named Joe Haxel who has a passive lander that he put out in our test site for a year, and that's at the north site, the one that I mentioned that's not grid connected. He gathered data for a year, and from that data, he can look at it and figure out what was making the sound. I kind of envision him sitting in his office being like CSI doing forensic analysis or something. But the left picture is a picture of a ship, and the right picture is a picture of a whale. So that he can look at that and say, oh yeah, that's a ship, that's a whale, this is what it looks like. And from that perspective, he can give us a sense of what's out around the test site and when it's around the test site. Here's a picture of his data that he took over a year. Now, the top row of data and the bottom row of data is the same data. The bottom row is just zoomed in. So if you look on the axis, the y-axis, on the top picture, he's measuring between 0 and 800 hertz. On the bottom picture, he's just zoomed into 0 to 200 hertz to really get a handle on what's happening there. And the reason why he's interested is look at the decibel levels across the top. Red means it's pretty loud, and he's seeing some red stuff at the low frequency levels, okay? So he looks at this chart, and what he's noticing is between the months of September and April, there's a lot of loud stuff down at the low frequencies. Anybody want to guess what that might be? Waves? Is that what you said? Whales. You think it's whales. No, it's not whales. It is waves. I was going to be really impressed that somebody guessed waves right off. Those are the waves crashing on the shore, and our test site is 2 miles from the shore. So that was really interesting when we found that out, because that level is up around 140 to 150 decibels, and if you can look at the bottom of the slide, 120 decibels represents marine mammal harassment levels. So this was a really interesting discussion to have with the regulators, that their levels of marine mammal harassment are lower than the waves are during the winter. And so this, rather than thinking this is just ridiculous, it motivates discussion that, hey, maybe those marine mammal harassment levels should be frequency dependent. Clearly, whales and dolphins and all the other guys who live in the ocean are fine with really loud noises at very low frequencies in the winter. So maybe it's very loud noises at higher frequencies that are a problem. And so this is one of the things that I find really interesting by being involved in these efforts, is the opportunity to have really great discussions with the folks who are responsible for what's happening in our ocean and scientists to help inform people about how we might move forward. Okay, I'm going to switch to tides. I don't have as much as on tides since I'm more focused on the wave side of the house. But as I mentioned, our University of Washington folks are focused on tides. Tidal energy in some sense is further along than wave energy, in the sense that we know what a tidal device should look like. The tides come in and they go out, or it might be going around an island. And what you're going to do is put a device in there that looks something like a wind turbine, but scaled for the tidal environment, scaled for the water environment. So something that spins maybe this way or maybe this way is going to be the kind of thing you're going to want to have to extract energy from the tides. One of the colleagues at University of Washington named Jim Thompson has been doing work both in Washington and in Chile, trying to categorize what different tidal resources look like. So just like we've been doing work on the wave resource, he's been doing work on the tidal resource. And on the top graph, what he's plotting is the speeds of the tides. He's plotting Admiralty Inlet, which is in Washington in blue, and Chacao in Chile in red. And what you notice is that Chacao has a higher speed of the tides going back and forth. But that's not the whole picture. It sounds like it's good, you're going to get more energy. The bottom picture is looking at the turbulence. And so when he's plotting the turbulence, Admiralty has lower turbulence than Chaco quite a bit. And what that's going to impact is that whole reliability and survivability piece. So it's not just, I want a lot of energy, but that has to be balanced with, will these turbines survive in the environment? Here's a picture of an open hydro turbine. This turbine is planned to go into Admiralty Inlet at a project by Snohomish Public Utility District. The Washington guys have been working with them. And if you look down, there's a little gizmo here right in front of the turbine. If you look kind of on the right-hand side, that's something called the AMP. It's an adaptive monitoring package that University of Washington has been developing for efficient environmental monitoring. It's going to have cameras, it's going to have acoustic measurement devices, it has a wet mate connector so you can just push it onto the foundation. We're going to be able to use it in our wave test facility too, and that's one of the things that the Washington guys are really good at. They've got a lot of engineers who are involved in the environmental side, and so by bringing these two areas together, they're able to engineer and develop new instrumentation that are really helpful for moving things forward. Here's a little bit what the AMP looks like, and for those of you who are really old Star Wars fans, they called the bottom the Millennium Tool Skid because they thought it looked like the Millennium Falcon. But you can there see how the AMP kind of wet mates into this docking station, and then we'll be able to gather information over a long period of time. It's going to be connected to the grid so you don't have a power problem. Anyway, just really nice advancement forward from the University of Washington folks. Just recently, I mentioned that we support testing from developers. They've been supporting this test of the ORPC tidal turbine. It went into Igiugig, Alaska about a month ago. And you can see it's really pretty turbulent there coming down underneath that device. It's about 30 feet long and about 5 feet high. And what we're hopeful about is that this will be, it's not as powerful as wave energy devices, but we're hopeful that it'll be producing enough energy that can really help some small communities in Alaska. Here's a video that he took of an acoustic hydrophone that's drifting over the device. Pretty soon you'll see the device. Unfortunately, you can't hear it. You can hear it how it gets louder and louder as it gets near the device, but this is a video from the GoPro camera. And the device is coming up soon, I think. There you go. So you can see it spinning. A lot of work has been done on that from the environmental side too. People were concerned that an animal could get hit by one of these blades turning. How would that affect the animal? So Pacific Northwest National Labs has been doing work on bruising. How bad would a hit be? And it turns out, maybe not too surprisingly, that the fish are kind of smart and they avoid these things. So having these kind of movies of what's going on is really helpful. And that's another thing we've been looking at both at UW and at OSU, is how can we do some in situ videos of these devices operating to try and get a handle of the environmental interactions. So a little bit on new directions. We're almost done here. Arnie had mentioned we're doing some work in offshore wind. We've got a couple of projects with Department of Energy and part of Principal Power, mostly looking at the environmental effects. So one of the things that we've been funded to do is look at bird and bat detection around wind turbine. Just as we're concerned with birds and bats with wind turbines onshore, what's going to happen when it's offshore? And onshore, it's not that difficult to set up monitoring systems, but what are we going to do when they're offshore to see what's happening? So some of our UW folks, some of our OSU folks have been working together to come up with camera systems that can work to see the interactions. Let me see if I can get this. Oh. Okay, let's try this again. There we go. Trying to develop infrared stereo tracking systems to quantify what's happening with birds and bats around these deployments. They're going to be working on this test system in October with the National Renewable Energy Lab in Colorado, which is where they do a lot of wind testing for onshore wind. They're also doing some work on the forces that bats and birds experience when they run into some of these blades. They've been doing some work with that down at there's a community college in Arizona, Mesa Lands. So they've been doing some testing on that there. So on that note, let me wind up and give you a summary of what we've been doing and where we're going to be continuing. NNMREC's expanding. We're expanding the kind of research we're doing. We're going to be doing more work on offshore wind. As I mentioned, we're moving into partnership with University of Alaska Fairbanks. You might wonder what they bring to the mix. Somebody asked me that today. They have a great test facility on in-river hydro. They've been doing work with that developer ORPC that I mentioned. And one of the things that we haven't been thinking too much about is what do you do if something's coming toward your device? This was asked of me at a community talk about a year or two ago when the Japanese tsunami happened and a Japanese dock ended up on the coast of Oregon. I said, what would happen if this Japanese dock was coming toward a deployment of arrays? What would you do? Well, the Alaska Fairbanks guys have been thinking about this in terms of a river and all the debris that comes down in the spring when the waters start flowing down after the melt. And they've developed a pretty nice device that you can think of it as having two pieces that come together, and when you detect debris, they're working to autonomously deploy this device and then close it up again. And so we're working with them to try and take some of these ideas and move them into the ocean and move them into the tidal regime. As you've seen throughout this talk, we do a lot of work trying to support developers, both with testing and with research. We want to continue to do that because that's the only way that we can make sure our research is really focused on the right issues. If we're just going to work in a vacuum without the developers, we can go do a lot of really interesting projects, but they might not be the right projects. The other thing that I talked about that we'll be continuing to do is the grid-connected test facility through PMEC. That's our PMEC South Energy Test Site. We're really excited that this will be the grid-connected test facility for the U.S. if it all works the way we're hoping it will. We've got several pieces of our regulatory work down the road. We're working on a cable routing study, and so that will be a really neat opportunity, not just for the developers to see what their devices do, but for the researchers to really get involved. I mean, where else can you do such hands-on environmental impact work? Where can you see how these devices are really operating and get some insights into the kind of things our engineering students are interested in? And then the last piece there is something that I've tried to touch on, is providing the scientific perspective to stakeholders and regulators. I could totally understand why stakeholders could be concerned about moving these devices into their water without knowing more. And so by being able to reach out to the community and understand their concerns, by being able to have the regulators educate us on what we need to be thinking about, and then do the studies that then educate them, it creates a really great synergy that can move the whole piece forward. And I would be remiss if I didn't thank all my NNMREC colleagues who gave me the material for this talk. We have more colleagues than this, but if you look through the talk, you'll see the work of these people. And with that, I'll thank you. Yeah, so there's so many different devices. The predictions are that this can get down to probably somewhere around 15 to 20 cents per kilowatt hour, which will be very competitive with what we're seeing with other renewable energy resources. If you wind the clock back maybe 4 or 5 years and talk to folks in Oregon about what we're going to see, they were very enthusiastic that we're going to put a test facility in the water and then we're going to have installations of 50 or 100 devices. You know, I said in passing that Ocean Power Technologies had a permit to do 10 and then they're going to do more. But if you look at where it takes to get from where we are today on a particular device to that really competitive cost of energy, and Oregon has really inexpensive cost of energy compared to a lot of other places because we have so much conventional hydropower, that picture doesn't quite ring true. And so I think what we're probably going to see happen is the devices going into the test facility and refining their performance, understanding how to increase their energy production. And then what we'll probably see is small deployments of these devices in the communities that really need them. Places like Alaska, places like Hawaii, where their cost of energy is 50 cents a kilowatt hour, $1 a kilowatt hour. Yakutat, Alaska is purported to be $1.50 a kilowatt hour. So a wave energy device that might be 50 or 60 cents a kilowatt hour sounds really great to them compared to what they're living with today with diesel. So that's what I think will happen. And as the developers go from an installation, test deployment to a small installation of devices and learn more, they're going to be able to make the engineering advancements that will bring that cost of energy down to the levels that I mentioned. And then we'll also see, as we get these different devices in the water, the ones that really are very efficient in terms of energy production, very reliable, low operations maintenance, all those pieces go into the cost of energy. Yes.
Just for reference, what would you say the cost per kilowatt hour is in a coal plant?
I have no idea what the cost of energy is. Do you?
4 or 5 cents a kilowatt hour.
4 or 5 cents a kilowatt hour.
Yeah, unless you include the cost of carbon.
Yeah.
Do you need to specifically design these devices depending on like where they are? Like, does it need to be designed specifically for that geographic place?
So, yeah, so the question is, are the devices designed for a particular geographic place? That's a great question, because one of the things I didn't really touch on is the difference between the shallow devices and the deep devices. So several of the Oyster device is near a shallow, it's in a shallow deployment, shallow being maybe 15 meters deep. There are a couple of other devices similar to in the technology type, that there's flappers that go back and forth that are in that same regime. There's a company called Resolute Marine Power, or Resolute Marine, I don't think the third word is power, but Resolute. They're going to test in Oregon. There's a place in northern Oregon off of the coast of Warrenton that's controlled by the Oregon Military Department, and there's some shallow water devices going in there. So that's an example of a shallow water device. The M3 device that operated by the changes in the pressure in the water column, that's about a 25 to 30 meter deep device. Our test facility, I mentioned the non-grid connected one was 45 to 50-ish meters deep. The grid connected site is going to be somewhere between 55 and 70 meters deep. So what the first thing you need to decide is what depth is right for your technology. And then another thing you need to decide is your technology able to withstand the vigorous wave environment of, say, Oregon or Humboldt or that kind of thing. Of course, if you don't go into a vigorous wave environment, you're not going to produce as much energy. So really the name of the game is you want to design to be in a really vigorous wave environment. And so you just need to figure out what that technology is. Now in terms of, would you go for a shallow water device or a deep water device? A little bit depends on how fast it gets deep off your coast. When we were looking for a test facility, the grid connected test facility, we started in northern Oregon and worked our way down to Coos Bay. And in northern Oregon, it gets deep so slowly because of the Columbia River dumping out there, that in order to get the depths we wanted, we would have been about 10 miles out, and then there would have been a fair amount of conflict with shipping and with fishing. But then if you go into southern Oregon, in Reedsport and Coos Bay, you can get that same depth at about a mile or two out. So there's a lot of variables involved with what kind of tech. So if you say, I have a technology, now where do I put it? There's a lot of variables involved in where I put it. If I turn that around and say, I'm a community who wants wave energy, what should I adopt? Then there are other things you'd look at depending on where you want it to be. Does that help? Okay. Question.
A few years ago, they were trying to put some of those devices in Humboldt, and there was a lot of opposition from the environmental side in regards to the cables and fisheries. Which device would you say would best suit around here with regards to like the fisheries and the cables because people didn't want to kind of, like you said, see them out there.
Yeah. So the great question, so was what do I think would go best here around the fisheries and cables issue? I'll answer that question drawing from what I've learned trying to site a facility. I think the first thing you have to do is talk to the community and understand what the community's interests are and what their concerns are. So, for example, if you found you had a community that had a very strong fishery, let me take crabbing, for example, a very strong crabbing fishery, and the ideal place from sort of the technical perspective to put this device was in that crabbing area, then you probably want to go back and rethink it. And so I don't think I can abstractly answer that question without knowing what specific concerns there were. And there's so many variables with how deep does it get, how close to transmission lines are you. But that, I guess that's my first point of guidance would be sit down with all the stakeholders and have a discussion about what works for them. When we were talking with the community of Reedsport, they didn't care about viewshed. They have a lot of dunes very near the coast, so there's not very many places in Reedsport where you see out into the ocean. So they didn't really care if it was a device that protruded up above the water very much. If you go up into northern Oregon, where you've got communities like Seaside and Astoria and some of those other ones where you've got a lot of tourism, they didn't want to see those devices. And this M3 device that's being deployed today is being deployed up there. And he's done a lot of community outreach with people, talking to them, what are your concerns? Is this okay? And he's gotten a lot of community support. So I think that's the first thing.
How much would you say does global warming and like low tide caused by that affect waters, like the water as a renewable energy source, the reliability?
Okay, so the question was the global warming and how the waters are affected by that. How does that affect the energy? Well, we're going to have, through the whole climate change, we're seeing more extreme events. We're seeing more storms. We're seeing communities where the waters are higher than they used to be. And so I think it's even more incumbent that these devices are reliable and survivable in these storm events if we're going to be seeing more of them. I personally think it's imperative that we start looking to low carbon energy sources to try and, I don't know if we can halt the changes that are happening, but at least not to exacerbate it. One of the things that I hear people, debates about the whole climate change thing, and is this a real thing or is it not a real thing? I'll tell you one thing that's a real thing, and that's ocean acidification. And ocean acidification is a byproduct of the whole carbon energy picture. And what's happening is measurable, and it's dramatically affecting some of our fish populations, and especially the sensitivity in the larval stage of things like oysters and clams and mussels, those kind of mollusks. So I think it's going to be really important that we do what we can to get away from the fossil fuels and embrace these other technologies. So if hand in hand with the climate change means our oceans are going to be more vigorous, let's look at how we can make these technologies more reliable so that we can embrace this other energy source. Yes?
How many of these devices, how many wave devices would be necessary to impact how strong the waves are hitting the shore in a significant way?
Okay, so how many of these devices are necessary to impact the waves that hit the shore? That's actually some work that's been going on at OSU. And again, the question is, it depends. that seems to be the answer to a lot of these questions, which is why it's really exciting being a university doing a research in it. It depends on several variables. It depends on how much energy the device extracts. It depends on how closely how close they are to each other, and how close they are to shore. So if they're kind of sparsely located and they're further from shore, the waves have a chance to kind of rebuild, and there's not this gap as they're hitting the shore. But again, it also depends on how close they are. So one of my colleagues in NNMREC has been busy looking at simulations of these kind of scenarios, trying to come up with predictive outcomes to answer those kind of questions.
Is that a bigger issue in Florida when they get with things like the Gulf Stream? Do they disrupt like major ocean currents?
Yeah. So the question is it more of an issue in Florida where they're doing the Gulf work and they could disrupt major ocean currents? Right off, I don't know the answer because I don't know the relative amount of the energy in the Gulf Stream compared to what they're deploying. But I do know it's one of the questions that they're asking about their technology, just as we are about our technology.
Are you looking at this technology as a way to power an entire city, like strictly off this, or as like a combination of solar and wind and all that?
Yeah, so the question is this technology that will be used solely to power a city or in conjunction with other things? I think it depends on where you are. I think that what you're going to see in a place, let's pick Yakutat, Alaska again. I think what you'd probably see, especially since this is in such an early stage, is they may put in some wave energy and then still have their diesel generation in case they need to use it in conjunction with the wave energy. So I think you're going to keep seeing these integrations of technology. And that's one of the other things that people are looking at with the whole marine energy, just like they are with other renewables, is how do you integrate them onto the grid? It's not an easy question, or it's not an easy question to answer. What I would hope to see eventually is that we totally get away from the fossil fuels and that you're integrating wave with wind, with solar, that kind of thing. Of course, whatever renewable you pick is going to be dependent on where you are. But I do expect in most places we will see some sort of patchwork portfolio. Although I can't say that for sure. I saw a question over here.
Has there been much research into the ecological impact of the electromagnetic field?
Boy, the ecological impact of the electromagnetic fields, and has there been much research? This is one of the questions that is a big conversation question. And if you notice, I said EMF was one of the big issues, and then I didn't say anything about it. The reason why is when we had the device out there, we tried to do EMF monitoring. And okay, so you're going to go out to do some monitoring. What kind of day are you going to pick? You're going to pick an ocean where it's nice. You're going to pick an ocean where the seas are like this. Pick a day where it's nice. So if you go out on a day that's nice, is the device going to be producing a lot of energy? No. So we didn't get anything on EMF. So that's one reason why I didn't show EMF. So the EMF is tricky because on the one side of the house, logically, there's a lot of power cables out there. And so shouldn't we know something because of the power cables that are out there already? As a scientist, my gut reaction to that is yes, we should. On the other hand, I think people are very sensitive of what might be different about these devices. Is it more than just the cables? Are the devices having some signature that might be different? So one of the things that I see in these early stages is we're doing some research and studies with the intent that eventually we'll take things off the table if we find there are non-issues. Sharon can tell you about a study that was going on with the Bureau of Ocean Energy Management where they looked at two cables that were in the water. One was powered and one wasn't, and they looked at the difference in the effects from that. So I think there are studies if you look for them. Part of the question is whether people trust them if you move the place. So if that was a study that was done in San Francisco, or if a study was done in Scotland, are people in Oregon or Alaska going to trust those studies? And that's another piece of it. Question.
Are you saying pushback power companies related to fossil fuels, or are they trying to help you with research?
So is there pushback from companies that are wedded to fossil fuels, or is there support for this research? Unfortunately, I'd say a lot of companies are ambivalent toward marine energy right now because I'm not sure if they believe it's reality. And so so it might be indicative of that we don't hear much from them. So I don't really see the pushback or the support. And I guess if I started seeing one or the other, that would be a good sign. Yes.
Can you talk a little bit about the roles that students play in, and whether individual
That's great. Yeah, so the roles that students play and whether the individual research projects interact or intersect with developers. So none of this research would be happening without students. If I make it sound like it's all the faculty doing it, then I totally misspoke. Because, of course, the faculty are guiding the students. I mean, it also doesn't happen without the faculty. It's a synergy. But Bob Pash and I have a group of about, it varies between about 4 to 6 graduate students at any given time. He's a faculty member in design. I'm a faculty member in dynamics and controls. What we find is some students will say, I want to design something, so they sign up to work with him. And then the next thing you know, they want to control it, so they start talking to me. This happened with a student who wanted to look at some power takeoffs. Or vice versa, the student who's doing the control on the vertical axis pendulum is my student, and then he wants to design things, so he talks to Bob. So, it is a give and take, but the students are the ones who are really moving things forward. We've got students in mechanical engineering, civil engineering, that's really where the ocean engineering side lives, electrical engineering, chemical engineering, oceanography, marine biology, public policy, so really a pretty good breadth there. Developers are involved in specific projects. There's, I could probably list off 3 or 4 developers who've worked with us where either the developer funds some work or the developer plus OSU or University of Washington goes to a funding agency and gets a grant. So they've been, a lot of the work with the developers have been around helping them understand a control system, helping them with testing, helping them with design of the device, that kind of thing.
So if these were, like I was saying earlier, if they were put kind of like in the town setting or was used for the town's energy source, how would it look? Would it be like one central facility with a bunch of devices, or would there be like how would that kind of look?
So I think if you were going to, so let's start on the small end of the scale. You might go to Yakutat, and there might be a kind of device where one of them could power the town. Now, that's not very robust, because if that device goes down, then they've got no wave energy. So I wouldn't advise that. I'd say at least put in 2. So let's move from Yakutat now. Let's move down to maybe a community in California. If you've got a lot of devices, maybe 100 devices, what you're going to have is some sort of cabling network that goes into some central hub system is what I expect. Now, I'm not an electrical engineer, so I don't know exactly what it demands, whether you'd have to have your own substation or that kind of thing, but it's going to be some sort of central network of cables bringing that power onto the grid. Is that what you're talking about?
Yeah, I was just trying to
Yep.
get a vision of like, because I saw your one slide where it was like if you talk about power supply at a time, but I was trying to figure out like maybe how many would be needed to power the town and what that would look like. Would there be some on like a certain side here and somewhere else?
Yeah, the whole point is that you'll want to get these devices onto the grid. So whatever makes sense in the grid structure in that town is what would dictate how that would go. And how many devices by, how much energy that particular device produces, and then how much energy the town needs. There's a, yeah. Yeah.
So sort of going off this conversation, so say you have an ideal area where they have an optimum amount of wave energy or tidal energy they can get, and you have the ideal amount of devices as well. Do you see this as something that has the potential to not only provide energy for that one town or city, or is that possibly something that would have to provide extra energy from other areas?
I'll summarize the question as this way. I think that will the devices be enough to only power the town, or will it produce enough energy that can do more? These devices will have enough ability that they could power probably most of the West Coast. Now, how far, I haven't done the calculation of how far in on the western states you could power before your electrons have all been used up. Do you happen to know, Bob, how far it would go?
How much of the coast you want to fill up the states?
Yeah, I mean,
if you want to fill up 1% of the coast, then you're not going to power the whole West Coast.
Right.
So it's a political question rather than a technical question.
Right.
But the Orkney Islands are net exporters of renewable energy to mainland Scotland right now. Between their wind, their tidal, and their wave, they're exporting power back to mainland Scotland.
Let's see. There was, yes.
Is there a map where you can go and see everything that's in the water? And since the water technically belongs to all of our sub-regions, is there something online where you can go and see everything that's been authorized to put into the water? I don't mean codes, but I mean installation.
Okay. So there's the first answer is there's nothing really out there right now. Because people keep asking me where are the commercial wave deployments, and there aren't any, and there really aren't any tidal ones. The very first tidal one has just been announced in Scotland. In terms of what's been licensed or permitted, probably the Federal Energy Regulatory Commission is where I'd head for the states.
I was thinking like an interactive thing that would show drill sites and it would show all the stuff that's in the water in particular areas, so that when you were trying to look at the environmental impacts, you'd be able to look at it all together.
There's a website run by Pacific Northwest National Lab called TETHYS, TETHYS, and we're thinking that maybe that's a place that you might find it. I actually don't know the answer. So I should have shown you my regulatory schematic. I think I've got 15 or 17 regulatory agencies on that schematic. So the question was, who do we deal with, and what's the relationship? So in terms of the relationship, we have something called the Collaborative Work Group. This started in January of last year, so 2013, and it has at the table every regulatory agency who officially and unofficially has a voice in this project. And then in addition to that, it's got stakeholder groups who have a voice in this project. So the listserv list is really quite long. So in terms of the regulatory agencies, the ones who are responsible for the project, like the lead roles, are the Bureau of Ocean Energy Management, because they control the federal waters, and that's where the project's going, so they tell us yes or no, you can have a lease. And then the Federal Energy Regulatory Commission, who license projects that connect to the electrical grid. And if you didn't have cooperation among the agencies, you'd have four or five different NEPA processes you'd be going through, and you'd have documents about this high in a stack instead of documents about that high in a stack, and it would be an extremely long process. Fortunately, the agencies are cooperating. So, for example, what I mean by that, BOEM, that I mentioned, and FERC have come together and done a process where they're doing this jointly. And so FERC leads everything, but BOEM's kind of their partner. So then you've got the agencies like NOAA National Marine Fisheries Service, who are responsible for making sure that we don't harass mammals and that we don't infringe upon endangered species. We have the Oregon Department of Fish and Wildlife, who don't have any jurisdiction over our ocean test site, but they've got jurisdiction over the territorial sea, and guess where our cables are being buried? In the territorial sea. And then they would have a voice at the table anyway, because National Marine Fisheries Service would ask them what they thought. And then we've got the Army Corps of Engineers, who control that we're putting anchors in eventually, and we've got environmental water quality, and Coast Guard for navigation, parks, because we're going to be going around parkland, near parkland, over the beach. Fish and Wildlife Service. I'm trying to click through my mind at who's at the table. Anyway, it's long and it's interesting.
What type of problems do you foresee in the future with this technology and integration into society?
So in terms of the problems as we go forward with this technology and integration into society, I think it's something we'll see evolve. You're going to have communities who want it now because they're desperate over their cost of energy, or they're very embracing of the marine technology because they see it as being part and parcel of who they see themselves as. They see themselves as a green community. They're in the marine environment. They want to go with it. There are communities right now who are staunchly against it. I expect as time goes on, their opinion will change as cost of energy goes up. If they're a fishing community, as their fish stocks are dropping because of acidification, as desperation sits in, as policy mandates it, I would hope that it becomes embraced as a positive thing, as a carrot rather than a stick, but it might end up being the latter depending on the whole time scenarios. I saw his hand. Oh, Colin?
One of the major issues I think that we have here at Humboldt is our port and the capabilities of our port, or the lack of capabilities for supporting and installing these devices, which can be huge and require very large docks and large cranes and floating cranes. Can you maybe just talk a little bit about how you address these challenges on your ports, because they're not much bigger than ours?
So the question's excellent about the ports and their capabilities or lack thereof. So I'll start out with a story, and this will tell Colin how well I've addressed this. Our Ocean Sentinel that I showed you there has anchors that are about 8,000 pounds each, 3 of them, and we deployed them last year. And we decided we'd leave them in the water to do a benthic study, see what happened over the year, see what our mooring systems looked like after a year, had our shackles disintegrated, et cetera, et cetera. And we were going to bring these up in May. And the boat that was going to bring them up had a contract in hand in February. Well, these are going to be there till next year because we can't find anybody to do it in the time frame or within the cost. If I wanted to pay $100,000 to pull these 3 relatively small anchors, I could get them out. But only being willing to pay $40,000 to pull these relatively small anchors, they are staying in. So that's how well we've addressed it, Colin. Now, let me give you a more positive answer. To answer that question, we hired a firm in Orkney, Scotland called Aquaterra to do a supply chain analysis of what we have and what it looks like. And what's really interesting reading this is he says, Oregon looks like Orkney did before we got marine energy. And he talks about fishermen that before they got marine energy weren't interested in doing any support work whatsoever. And some of those same fishermen now own 3 multi-cats, which are really great multi-purpose vessels for putting things in the water and pulling things out. They've got flat platforms and they've got cranes and really great capabilities. And then, you know, Orkney didn't have a particularly great pier. You go there now and they've got a pier to knock your socks off. Now, granted, they've had huge federal, state, and local investments, whatever the right words are for them, which has helped them a lot. But they've also had community investment, communities stepping up to do this. And so that's, you know, it's hard to motivate the state or local government in Oregon to buy a great vessel for operations when all we're talking about are 3 dinky anchors for our Ocean Sentinel. But they're beginning to hear more. M3 just deployed in northern Oregon, and Resolute is going to deploy. And as you have these people saying, hey, if the state invested $3 million in one of these vessels, it would be able to do all this work. It would be able to help dredge the ports. I think that you're then able to make the case and get the funding to start building up the infrastructure. So what my buddies in Scotland basically say is, don't worry, Belinda, it'll happen. But, you know, the time will come, the money will come, it'll happen. So hopefully they're right. So I would say, Colin, don't worry, the money will come, it'll happen. Yes.
I was wondering if you knew the sound frequency that these machines tend to offer.
The sound frequency of these machines?
Yeah.
It varies again on what it is. There's so much difference in size, and whether you've got something that's going up and down versus something that's rotating and going around, or if you think about the M3 device that's just having these airbags depressed, it varies a lot.
Maybe one more question to wrap up.
Oh,
I was going to ask a question about sound, actually. you had a plot where you showed the sound produced by the waves, right? And in that, most of the high decibel was sub 10 hertz. But then there was, for a few periods of time, it seemed like bands at 25 hertz or 50 hertz. And it was like clear bands. I'm just wondering, is that due to the same?
Okay, so you're talking.
Like September the 19th. It's like there's clear bands, horizontal lines going across it, which seems sort of odd to be attributed.
That's a fishery, but I don't know which fishery operates that time of year. But that was
So
that's the ships that went with went with the fisheries. And because there's another peak.
So we may be looking at two different types of engines.
I think these are the crabbers. I think that's what I was told. Is this is the crab fishery. But I don't know. Does anybody know who goes out and fishes in September and October? Could that be a salmon fishery of some sort?
Back earlier in the year as well.
Yeah. So I'm wondering if maybe there's some. Oh, in fact, I do know that there is a frequency that our EMF guy picked up on a boat that was about at 50. So I bet that there's something common to some of the ships around 50.
It looks like it's there for a large part of the year, just not quite as loud.
Well, and see, that would make sense because our site is not very far from Newport. And so there's a big fishery in Newport, and as they're going out and turning north, they're going right by our site. So I would, not knowing any better, I would conjecture that there's a sound associated with the fishing fleet.
It might be their black boxes, like their detection. I can't remember what it's called, but they're monitored with them.
Yeah.
What about log exports, bigger ships? Maybe.
Yeah, I don't know. My guess is it could be some other export ship as well. But anyway, I expected it's a ship.